So let's look at some sines and cosines, and then we'll do things. So let's say we want to integrate, say, where do I start here? Sure, let's start with an easy one. Let's do sine cubed x times cosine x dx. So we're trying to integrate sine cubed times cosine. We're going to do a u substitution, and we're going to select u to be one of the trig functions. And in this case, you can actually pick either one, it'll work out fine. But the easier choice, if both powers are odd, is typically to pick u to be the trig function to the higher power. So if we select, raise this up here. If we let u equal sine of x, our du is going to be cosine of x dx. And then we can totally rewrite this as, well, there's my du right there. And sine cubed will become u cubed. So this will be equal to the integral of u cubed du, which will then be just u to the fourth divided by 4 plus c. And then we'll place u with sine, and we'll get sine to the fourth x over 4 plus c. Well, let's see how this problem changes somewhat dramatically if we increase the power on cosine. So let's say instead of sine cubed times cosine, let's say we have sine cubed times cosine squared. That's a cosine squared dx. So now things are going to be a bit different, actually. So you might think we could let u equal sine again, and actually that's not going to work here. And the reason it's not going to work is because if we let u equal sine, our du is going to be cosine. But we're still going to have a leftover cosine. So this is not the right way. This is the wrong way. The wrong way would be to let u equals sine of x. Then our du would be cosine of x again. And if I rewrite this, I have the integral of sine cubed x times cosine x times cosine x. I kind of like to peel off the du. And the problem here is, well, great, there's my du. There's my u cubed, but what am I going to do with that cosine x? It's a problem. And so here's kind of what we want to do when we have powers of sine and cosine. You want to choose u to be the thing. This is kind of a wordy way of saying it, but you want to make a choice for u so that after you dealt with du, there's an even amount of the non-u choice. So what I'm saying is if I pick u equal to cosine, I want there to be an even amount of sine left over after I've dealt with changing dx to du. And there isn't. There's an odd amount. Also, additionally, right, the problem with the extra cosine is problem. On the other hand, if we pick u equal to cosine of x, well, then our du is going to equal negative sine of x dx. I'm going to adjust for a minus sign, so minus du is going to equal positive sine of x times dx. And when I start rewriting this, if I break off one of the signs, I have the integral of sine squared x times cosine squared x times sine x dx. All right, same thing as sine cubed times cosine squared. I'm just rewriting it in a convenient way. This sine x times dx is my negative du. Cosine squared is u squared. And the reason I want an even amount of the non-u choice left over is because I can use a trig identity. So we can use the fact that cosine squared x plus sine squared x is equal to 1, and then isolate sine squared. So sine squared x equals 1 minus cosine squared x, to replace this with 1 minus cosine squared, which is going to be 1 minus u squared, because we chose u equal to cosine. And then we can rewrite this as the integral of 1 minus u squared times, I'm going to write this as u squared times negative du. I'm going to say that's a negative u squared times du, just to make it a little easier. And if we multiply it out, we have the integral of negative u squared plus u to the fourth du. We integrate, we get negative u cubed over 3 plus u to the fifth over 5 plus c. And then we're going to end up with negative cosine cubed x over 3 plus cosine to the fifth x over 5 plus c. So that's kind of the idea, is you're going to pick, if you've got powers of sine and cosine, we're going to pick u to be the thing so that there's an even amount left over of the non-u choice. Specifically, when you're dealing with sine and cosine, if one of them is to an odd power and one of them is to an even power, you're always going to pick u that's equal to the 1 raised to the even power. So let's do 1 or 2 more examples of this and then we'll move on. So let's say we had the integral of cosine to the 6th x times sine to the 5th x. This one's going to be a little gross. That's okay. So again, just like last time, I'm going to pick u equal to the thing that's to the even power. So I'm going to pick u equal to cosine of x. My du is going to be negative sine of x times dx. And I'm going to say that negative du is equal to positive sine of x times dx. Rewriting this. So whenever I'm rewriting this, I'm always going to break off my du part here. So I'm going to rewrite this as the integral of cosine to the 6th x. And then instead of writing sine to the 5th, I'm going to write sine to the 4th times sine. So sine to the 4th x times sine x dx. There's my du. Sorry, there's my negative du. There's my u to the 6th. For sine to the 4th, I have to be a little extra careful. So we know that sine squared x is equal to 1 minus cosine squared x, or in this problem, sine squared x equals 1 minus u squared. So then sine to the 4th is going to be sine squared squared. So that's going to be 1 minus u squared squared. It's a little messy, but it's fine. So we have a, whoops, write that in red. Here we have a 1 minus u squared squared. And then it just becomes a big algebra problem. So we've got the integral of negative u to the 6th times 1 minus u squared squared. We have to multiply this out. So it's going to be negative u to the 6th times 1 minus 2u squared plus u to the 4th du. And then that's going to be the integral of negative u to the 6th plus 2u to the 8th minus u to the 10th. And then we integrate and we get negative u to the 7th over 7 plus 2u to the 9th over 9 minus u to the 11th over 11 plus c. And then we plug back in cosine. We get negative cosine to the 7th of x over 7 plus 2 times cosine to the 9th of x 9 minus cosine to the 11th of x over 11. Oof. All right. The only other thing, and I don't know if you're responsible for knowing this or not, but I'm just going to mention it. If both sine and cosine are raised to even powers, you cannot do a u substitution. So for example, if you were asked to just integrate cosine squared x, the way you integrate just an even power of cosine or an even power of sine or a multiple of them together is by rewriting it with the trig identity. This is the integral of 1 plus cosine of 2x all over 2. So fun fact, cosine squared x equals 1 plus cosine of 2x all over 2. And sine squared x equals 1 minus cosine of 2x all over 2. So if you have just even powers of sine and cosine, these are the identities you have to use. And then it's not too terrible. We're going to factor out the 1/2 with the integral of 1 plus cosine of 2x dx. And then the integral of 1 is x. The integral of cosine of 2x is sine of 2x divided by 2. And then you can distribute the 1/2 if you really want to. 1/2 x plus sine of 2x over 4. These particular problems do get progressively worse if the even powers are higher. Meaning, if you had the integral, say, cosine squared x times sine squared x, you do have to replace both of them with their identities. So that's going to equal the integral of 1 plus cosine of 2x all over 2 times 1 minus cosine of 2x all over 2. I would factor out the 1/2. So I have a 1/4 integral of 1 plus cosine 2x times 1 minus cosine 2x. This one is kind of nice in that when you multiply this out, the middle terms cancel. So you end up with 1/4 the integral of 1 minus cosine squared of 2x. If you really want, you can change this to sine squared, right? Because 1 minus cosine squared is equal to sine squared. Most people often actually do that. So we can rewrite this as the integral of sine squared of 2x dx. And then we're going to use that identity again, but now instead of saying sine squared of x is equal to 1 minus cosine of 2 times x all over 2, we're going to say sine squared of 2x is equal to 1 minus cosine of 2 times 2x all over 2. And then we factor out the 1/2. So it's 1/8 times the integral of 1 minus cosine of 4x. And then that's going to be 1/8 times x minus sine of 4x all over 4. They're kind of gross. And then I suppose 1/8 x minus sine of 4x all over 32. But basically, if you have powers of sine and even powers of sine and cosine, you just keep doing this until you get down to something you can actually integrate. Yeah. So powers of sine and cosine, that's it. If one of them's odd and one of them's even, you let u be the one that's raised to the even power. If they're both even, you do this terrible thing. If they're both odd, you pick u equal to the one that's the higher power, just because it's easier algebra. All right. I suppose we should do a couple examples with secant and tangent as well, just because they might show up. So I want to integrate secant, not bounds, secant squared x times tangent cubed x dx. So just like with the sines and cosines, you want to make a choice for u so that the remaining non-u choice has an even power. So if I pick u equal to secant, I want there to be an even number of tangents left over after I deal with du. See, similarly, if I pick u equal to tangent, I want there to be an even number of secants left over after I deal with du. And I think this one actually works either way. So let's check it out. If I pick u equal to tangent seems like a real good choice. If u equals tangent, my du is secant squared x dx. Yeah, that's kind of ideal, because then this is just going to become the integral of, well, there's my du right there. It's secant squared times dx. There's my du. So I'm just going to have u cubed du, which is going to equal u to the 4th over 4 plus c, which is going to be tangent to the 4th x over 4 plus c. But I will point out, this one would also work if we did a different u substitution. We could let u equal secant x. Now doing it this way is going to be more work, but it's worth seeing the process. So if u is secant x, our du is secant x tangent x dx. So I'm going to rewrite my integral as the integral of, I'm going to break off the secant x tangent x. So I'm going to write this as secant x times tangent squared x, pulling off the secant and the tangent, and then times secant x tangent x dx. So check it out. There's my du. There's my u, and I have an even amount or an even power of my non-u choice left over. So then I use the identity for tangent and secant, which is everyone's favorite. And I'm sure I've said this in class before, but I'm going to say it again because I can't help it. It's I tan and get sexy. Unforgettable. So then if we solve for tangent squared, tangent squared x equals secant squared x minus 1. So in this particular problem, the tangent squared is going to be equal to u squared minus 1. So then we've got the integral of u times u squared minus 1 du. So again, you doing all right, Devin? Oh no, I'm sorry. If you need to use the restroom, you're more than welcome to go excuse yourself. But okay, so make sure you're doing all right. If we multiply this out, it's going to be integral of u cubed minus u du. So we're going to get u to the 4th over 4 minus u squared over 2 plus c, which is going to equal secant to the 4th x over 4 minus secant squared x over 2 plus c. I will fully admit these answers look very different. They are the same. They might differ by a constant, but if you use trig identities, you could totally get from this to that or vice versa. Like if you replace tangent squared with secant squared minus 1 in this integral here, and then squared it out, you would get essentially the same answer here. It'd probably different by a constant, but that's okay when you do integration. And let's do one more, and then we'll move on to this 16B final review, which has lots of fun stuff. So let's say we have, let's look at the integral of secant to the 5th x tangent cubed x. And I'm pretty sure this example only one way will work. So let's look at the wrong way first. If I pick u equal to tangent, what's my du going to be? I think secant squared, right? So if my du is secant squared, I'm going to peel off 2 of the secants from secant to the 5th, but then there's going to be a secant cubed left over, which is not good, because if there's a secant cubed left over, my non-u thing, there's an odd amount, and I want an even amount. So u equals tangent here is not the way to go, because your du would be secant squared x, and that's just not going to work out. So in this one, we need to pick u equal to secant x. The reason being, our du is going to be secant x times tangent x dx. And the thing that's not my u, so tangent in this case, after I deal with my du, there's going to be an even amount of tangent left over. So I'm going to rewrite this as the integral of secant to the 4th x times tangent squared x times secant x tangent x dx. And then we see all the things. We have a du, we have our u to the 4th, and tangent squared, well again, tangent squared x equals secant squared x minus 1. So in this particular problem, tangent squared x is going to be u squared minus 1. So then we're going to get the integral of u to the 4th times u squared minus 1 du. Multiplying it out, if we're integrating, we're going to have the integral of u to the 6th minus u squared, which will then be u to the 7th over 7 minus u squared, u cubed over 3 plus c, which will then be secant to the 7th x over 7 minus secant. I feel like I made a mistake. Yeah, that u to the 4th multiplied out should be a u to the 6th and a u to the 4th, not a u squared. So that means we should have this u to the 5th over 5. Good thing my 3's and 5's are so similar. So we're going to have secant to the 5th x over 5. I was just about to comment that if you do a problem like this, it should be the case that essentially all your powers of secant or sine or cosine or tangent or whatever you end up with, and all the powers should be the same parity, meaning they should all be odd or all be even, and they should all typically differ by 2. So the fact that I was getting secant to a lower power, that was like, that's problematic. So that's kind of it as far as integrating powers of sine and cosine or secant and tangent. You almost always let u equal one of the trig functions. Your du is something, you take care of that something, and then you really, really, really want an even amount of the non-u choice left over. And then you often have to use a trig identity. Anyone have any questions about that? As I point at you, I'm pointing at the camera. There's something else. Good. Just in case you didn't get it, here is the attendance form again. Yeah, all right, cool. All right, let us look at this final review. So we'll do this today and Thursday. I mean, I assume we'll probably get through it before Thursday, but we'll see if we don't, or if we do, then I've got other things to do. But it's just kind of a smattering of things, kind of to refresh our memories about all the stuff we did. So let's look at this first one. The integral of x cubed plus, I believe these are posted on Canvas and solutions. If they're not, I would have post them up there. But I think they're already up there. So as I could look, I literally have a computer right in front of me. So we have the integral of x cubed plus 6x squared plus 2x plus 3 over x squared plus 6x plus 1. And already this looks not very promising. Well, I shouldn't say that. Here's why I think it looks not promising. I'm observing that denominator doesn't factor, which is worrying to me because I know I'm going to have to do polynomial division, and then usually after polynomial division, partial fractions is often where we end up. But I'm guessing that's not going to be the case here. So I guess what I'm saying is I'm looking at this and thinking about what's going to happen. Well, I should probably just get to the point and do the polynomial division, because when your degree on top is greater than or equal to your degree on the bottom, polynomial division is almost always where you start. So let's do the division. X squared plus 6x plus 1 is going into x cubed plus 6x squared plus 2x plus 3. So we multiply x squared by x to get x cubed, and then x times 6x is 6x squared, and x times 1 is x. So that's convenient. Maybe this problem's going to work out nicely. So we subtract x cubed minus x cubed is 0, 6x squared minus 6x squared is 0, and 2x minus x is x plus 3. And we actually are done, right? There isn't another step to do because we didn't get an x squared term. So we can rewrite our integral as the integral of x plus the remainder divided by the divisor. Now this is where this problem would be trickier if someone if someone had made it so that the denominator was like x squared plus 6x plus 5. So like, let's just say on the side here, if we had this problem instead, the integral of x plus 3 over x squared plus 6x plus 5, it would be very, very tempting to try and use partial fractions here, because that denominator definitely factors, right? This is equal to x plus 5 times x plus 1. And you totally could use partial fractions there. And you shouldn't. Because as I like to say, partial fractions is a method of last resort or later resort. You should exhaust other easier methods first. And definitely here, we can do a u substitution. We can let u equal x squared plus 6x plus 1. And our du is exactly 2x plus 6 dx, which is 2 times x plus 3. So 1/2 du is equal to x plus 3 times dx. And we can rewrite this as, I would probably do it this way. I would do the integral of x, so I'm going to get x squared over 2 plus the integral of, this is going to become 1/2 du over u. And then that's going to be x squared over 2 plus the integral of 1/2 du over u is 1/2 the natural log of the absolute value of u. And then that's going to be x squared over 2 plus 1/2 natural log of my u, which is x squared plus 6x plus 1 plus c. Yeah. Questions? Okay. Questions from the Zoom? All right. Let's look at the next one. Where'd you go? So that was problem 1. Maybe I should numbers just from practicing again. or final review, I should say, not a practice exam. Also, if you're a teacher, I imagine the teacher is probably maybe going to post practice exam. Might I'll look. I'm on her campus as well, so I'll take a look and see if there's something that she has for you all to look at. I will certainly look at that as well and use it if it seems reasonable. So the next one is the integral of x plus 2 over x cubed plus x squared. And even though I know it's going to be partial fractions, I should at least think about, could I do a u sub here? Does it make sense to let u equal the denominator? Not really, right? If u equals x cubed plus x squared, our du is 3x squared plus 2x, and that's not really gonna help. So no. But I really want you to be in the habit of looking for a u sub before you do something else crazy. Right? Think just like, does a u sub make sense? Could it possibly work? Okay, it doesn't. Let's move on. So this is looking like partial fractions. It's going to be the integral of x plus 2 over, I can factor out an x squared times x plus 1. So how many fractions is my partial fraction decomposition going to have? 3, exactly. Good. Sure. So here's what I'll say. I would say that, so the question is, can I remind you, when do we use u sub or integration by parts? So I would come at any integral with u sub is always on the table, right? I'm going to look for an easy u sub. That's just like the place I want to start. I'm always hoping that u sub is going to work because u sub is typically straightforward. As far as integration by parts goes, I know that this is not a good candidate for integration by parts because it's not a mixture of functions. I have powers of x, but I don't have a logarithm or an exponential or a trig function. Usually I want some combination of at least 2 of those things. Like I want a trig and a power of x, or a logarithm and a power of x, or a trig and an exponential, right? I want at least 2 of those things to show up to even really consider integration by parts. So that's how I knew that integration by parts wasn't in the running here, because all I had was powers of x. So if all I have is powers of x and u sub isn't going to work, then partial fractions, if it meets the criteria, right? If it's a rational function whose degree on top is lesser than the degree on the bottom and whose denominator factors, then I can use partial fractions. So let's see, I'm gonna write this as a over x. Let me actually be sure. I just wanted to follow okay, that's fine, yeah. Plus b over x squared plus c over x plus 1. I do think it's worthwhile to actually write out that you are multiplying both sides by the common denominator x squared times x plus 1. This makes it easy to make sure you don't make any mistakes. So when I multiply this by that, we of course just get x plus 2. When I multiply this by that, we get a times x plus 1. We multiply that by you get b times x plus 1. Multiply that there, you get c times x squared. And I'm always a proponent of picking the convenient values of x. So any value of x that makes one of these factors 0 is good. So let's try x equal to 0. So I'm going to get 0 plus 2 on the left equals a times 0 times 1 plus b times 1 plus c times 0. Oh, I get 2 equal to b. Great. Let's pick x equal to -1. So on the left, I get -1 plus 2. On the right, I get a times -1 times 0 plus b times 0 plus c times -1 squared. So -1 plus 2 is 1, and c times 1 is c, so c equals 1. So now I've run out of convenient values of x. And there's 2 ways you can approach this last part. You can either just pick another value of x, because there's only one thing left. There's only one thing left to find. Picking one more value of x is usually pretty easy. So we could pick x equal to 1, and then plug in for x again, and also plug in your values of b and c. So I have 1 plus 2 on the left equals a times 1 times 2 plus b is 2, so it's 2 times 1 plus 1 is 2, and c is 1, so it's 1 times 1 squared. So then I get 3 equal to 2a plus 4 plus 1. So that's 5, so 3 minus 5, so I end up getting -2 equal to 2a, so I get a equal to -1. That's not my preferred way of doing it, but it definitely does work if you're just trying to find one last constant on top. The other way you could do this would be to equate coefficients. You can look for the highest power of x on either side, which is x squared. And you can say, okay, so for x squared on the left, I have 0x squared. On the right, I have an a times x squared. I don't have a b times x squared, but I do have a c times x squared. So that tells me that 0 is equal to a plus c, which tells me that a is equal to -c, but c is 1, so a is equal to -1. That's the way I usually do it, but either way is fine. This way is more better, more good. This is what I use really if there's still more than one thing left to find. So if I had found the first two values using these convenient values of x, and then there was still like an a and a d left to find, usually it's easier to then just start equating coefficients as opposed to plugging in more and more values for x. So then we can integrate this. This is going to equal the integral of a over x, -1 over x, plus b over x squared, so 2 over x squared, plus c over x plus 2, x plus 1. So that's going to end up being the integral of -1 over x is negative natural log of the absolute value of x. The integral of 2 over x squared, which I'm really thinking of as 2 times x to the -2nd, is 2x to the -1st over -1. And then the integral of 1 over x plus 1 is the natural log of the absolute value of x plus 1 plus c. And then I would never leave this like this, right? I would definitely rewrite this as negative natural log of the absolute value of x minus 2 over x plus the natural log of the absolute value of x plus 1. Let's see. It's not wrong to leave it like this. It just feels so unsimplified that it just hurts my heart to leave it like that. So I have to change it. But you can probably like that test and be okay. But you shouldn't simplify that. It's super easy to simplify. All right. So now let's look at this next one. Let's look at the integral of the natural log of x over x cubed. So this is what I would call a mixture integral, right? There is a mixture of different types of function. I have x to a power and I have a natural log of x. So this to me says either it's going to be a u sub or it's going to be integration by parts. And I'm always going to look for the u sub first. So could I do a u sub? So if I let u equal the natural log of x, the du is 1 over x dx. And that's not great because I have a 1 over x, but then I'm still going to have an x squared left over. So unless my u sub is working out pretty nicely, it's probably not the path I want to take. Instead, I'm going to try integration by parts. Now, the funny thing here is that for integration by parts, I'm still going to make the same u choice. That's okay. So I probably didn't need to cross that out. So u equals natural log of x. Du is 1 over x dx. And then dv is the rest. So if u is natural log of x, dv is 1 over x cubed times dx. Or if you prefer, x to the -3rd times dx. And I do prefer because that makes it easier to anti-differentiate. So then our v is going to be x to the -2nd over -2 times dx. Or I might write it as -1 over 2x squared dx. Okay, so now let's do the thing, right? We want the integral of natural log of x over x cubed. It's going to equal uv minus the integral of v du. So in this particular setup, that's going to be the natural log of x times the -1 over 2x squared. Oh, that's not right. Is it? Oh, it is right. I just did something stupid. I wrote a dx here. There shouldn't be a dx there, right? I was like, wait, there's a dx? No, there's a dx. Okay. So u times v minus the integral of v, so -1 over 2x squared times du, which is 1 over x dx. And then we need to rewrite this integral so we can see that it's actually easy to integrate. So here I'm going to have negative natural log of x over 2x squared minus a minus. So I'm going to bring out the minus 1/2 and say I have plus 1/2 times the integral of 1 over x squared times 1 over x is 1 over x cubed. Well, great. We just did the integral of x to the negative third. It's x to the negative second over negative 2. So this is going to equal negative natural log of x over 2x squared plus 1/2 times x to the negative second over negative 2. Let's see. Or simplifying it in a more normal way, negative natural log of x over 2x squared minus 1 over 4x squared. Let's see. Some people like getting a common denominator here. I definitely do not. I do not think that's necessary. This almost always works out this way when you have like the integral of natural log of x times the power of x. You're almost always doing this thing where you let u equal natural log, dv is the rest. You do integration by parts, and then the integral you end up with ends up essentially being the same thing you already did for dv. It almost always works out that way. It's kind of nice. Questions about this one? Okay. So yes, again, just to point out, right, when I have a mixture like this, where I have a logarithmic function times a power of x, right, I'm thinking it could be u sub or it could be integration by parts. I'm going to look for a u sub first because, again, u sub in my mind is typically easier to do than integration by parts. Let's look at the next one. The integral of x plus e to the 3x quantity squared. So I would agree that this is a mixture, but it's not going to lend itself to any method we like. There's no good u sub here. If I let u equal x plus e to the 3x, my du is 1 plus 3 to the 3x. That's not good. And when I say mixture, there's really more to it than that. When you're looking for mixture, if you're thinking u sub, you should be like, okay, well, the inside of something should be my u and its derivative should show up. Whereas if I'm thinking integration by parts, it has to be things that are multiplied together, right? You can't just have, like, if things are added together, it's not a mixture that where integration by parts is going to work. So what I'm trying to say in the longest way possible, apparently, is we need to multiply this out. So let's see what happens when we multiply that. So multiplying it out, I've got the integral of x plus e to the 3x times x plus e to the 3x. I'm going to get the integral of, let's see, x times x is x squared. I'm going to have an x e to the 3x plus another x e to the 3x. So I'm going to have a 2x e to the 3x. And then e to the 3x times e to the 3x is e to the 3x plus 3x, which is e to the 6x. And two of those pieces are really not terrible. I'm going to rewrite this as the integral of x squared plus e to the 6x. That's going to be just fine. We can deal with that. And then we're going to have the integral of 2x times e to the 3x. And now we have a mixture where integration by parts does make sense. We have 2x times e to the 3x. So when you have a mixture and things are multiplied together, that is often when integration by parts is good. And we'll point out, if this was 2x times e to the 3x squared, then the u sub would be what we want. We would let u equal 3x squared, and our du would be some multiple of x. But here, 2x times e to the 3x, making u equal to 3x is not going to help out. We need to do a integration by parts. So let's see. So I'm going to let u equal, let's see, late. I don't have a log, so I'm going to let u equal the algebraic or the any power of x. So I'm going to let u equal 2x. My du is 2dx. The 2, believe it or not. My dv is the rest. It's e to the 3x dx. And my v is the antiderivative of that, which is e to the 3x over 3. So then rewriting this, let's also integrate this as we go. So the integral of x squared is x cubed over 3. The integral of e to the 6x is e to the 6x over 6. And the integral of 2x e to the 3x is uv minus the integral of v du. So it's going to be uv, so 2x times e to the 3x over 3 minus the integral of v du. So the integral of e to the 3x over 3 times 2 dx. Well, that's not too terrible. That's going to be x cubed over 3 plus e to the 6x over 6. I'm going to write this as 2/3 x e to the 3x. And then here I'm going to get minus 2/3 times the integral of e to the 3x is e to the 3x over another 3. I suppose you could simplify that last part and write it as 2/9 times e to the 3x, but I don't think you really need to. Ooh, that was nice. Okay. Questions, comments, concerns? Nope. All right. Moving right along. For those of you on Zoom, do like if you have a question or a comment, you're welcome to speak up or write something in the chat. A couple of you have already. Thank you. I always like questions. Let's look at the next one. So we have the integral of x times secant of 3x squared. Again, I see a mixture. I have a power of x in a couple places and a trig function. So here I have to ask myself, okay, u sub or integration by parts. Well, I'm always going to think u sub first. So is there a good choice for u? Yeah, there is. We let u equal 3x squared. The du is going to be 6x dx, which I essentially have. I guess I should point out really, right? The difference here is that here, when I'm looking for u substitution, I'm looking for the u to be kind of inside some other function, and then its derivative is somewhere else, right? Whereas in the previous problem here, when I'm doing integration by parts, my u and my dv are multiplied together. There isn't like a u that's inside another function I can really pick that makes sense here. So adjusting my du a little bit, I have a 1/6 du is equal to x times dx. So, right, there's my 1/6 du. There's my u. So I can rewrite this. Oh, this problem might be kind of, we'll do this, but this problem's a little, I don't know if we've actually talked about this, so we'll go there. This is going to equal the integral of 1/6 times secant of u du, which is 1/6 the integral of secant of u. I'm not sure if we've talked about the integral of secant in this class though. If you haven't, that's okay. If you're probably not responsible for it. I will tell you, it is something that people memorize. The integral of secant of u is the natural log of the absolute value of secant of u plus tangent of u. If that doesn't sound familiar, I wouldn't worry too much about it because you probably haven't learned it in class and you're probably not responsible for knowing. But if you are concerned, you have questions, you are welcome to ask. So then we're going to plug back in u and get 1/6 natural log of the absolute value of secant of 3x squared plus tangent of 3x squared. But yeah, kind of forgot that. Does this look familiar to you? Yeah. Okay. Well, I don't think we've talked about it in this class. So if you've talked about it in Burke's, then okay. In a second, after we do this next one, I can run down. We cannot solve this with integration by parts. Actually, it's a really good question. So it wouldn't work to use integration by parts here, because when you use integration by parts, you want to pick u to be a thing that's going to get simpler when we differentiate it, and you want to pick dv to be the rest, but dv also has to be kind of relatively straightforward to anti-differentiate. And the thing here is that you could pick u equal to x, and then your dv would be secant of 3x squared. I don't know what the integral of secant of 3x squared is. It might not be integrable. On the other hand, if you pick u equal to secant of 3x squared, its derivative is going to get way more complicated. The derivative of secant of 3x squared is going to be secant of 3x squared times tangent of 3x squared times 6x. It's not getting better. So definitely not integration by parts. It really is a u sub problem. In contrast, let's look at this other one. So I'm going to try and we'll keep this over here for a second. So, oh, that was the problem. So let's look at this problem that looks very similar, but is quite different. The integral. Place here. Let's look at the integral of x times secant squared of 3x. Yes. Looks pretty similar to the previous problem, right? The previous problem was x times secant of 3x squared. Now we're doing x times secant squared of 3x. And here is actually where it is going to be integration by parts, because there isn't a good u sub. Right? If I pick u equal to 3x, my du is 3. I mean, that doesn't really help. Quick aside, if you're doing u sub, picking u to be x or a multiple of x doesn't really get you anywhere. That's not entirely true. Right, back in the day, we definitely did like the integral of e to the 6x dx by doing a u sub for u equal to 6x. But now we just know that that's going to be e to the 6x divided by 6. Okay, so for this one, u sub seems not great, so let's try integration by parts. So again, when you're doing integration by parts, well, we know we pick u according to the late acronym typically. Although I would also point out, picking u equal to x, great, gets simpler. Picking u equal to secant squared would be bad, right? The derivative of secant squared of 3x is even worse. It's like 2 times secant of 3x times secant of 3x times tangent of 3x times 3, right? That's terrible. We don't want all that. Additionally, the antiderivative of secant squared is really not bad, right? Secant squared's antiderivative is just tangent, so that's good. So we're going to let u equal x, our du is going to be dx. Our dv is the rest, secant squared of 3x dx. And the antiderivative of secant squared of x is tangent of x. So the antiderivative of secant squared of 3x is tangent of 3x divided by 3. So that looks not bad, right? Things got simpler. Yeah, we're looking good. So then our integral of x times secant squared of 3x dx is going to be u times v. So x times tangent of 3x over 3 minus the integral of v du. So tangent of 3x over 3 dx. I'm going to rewrite this a little bit. Write it as x times tangent of 3x all over 3 minus 1/3 the integral of tangent of 3x. I'm pretty sure we've talked about the integral of tangent. Here it is again. So the integral of tangent of x is the negative natural log of cosine of x, or the positive natural log of secant of x. I'm going to go negative. So it's going to be the negative natural log of cosine of 3x divided by 3. The whole thing divided by 3. So then if I was going to write this out, I would say I have x times tangent of 3x all over 3. Minus times a minus is going to be plus natural log of cosine of 3x in absolute value, all divided by 9. This feels like a good moment to remind ourselves, or maybe see for the first time, all the antiderivatives of the trig functions. So here's a quick recap of trig functions. And we'll do, I'm going to write a few things here. So let's talk about all the derivatives first, just to remind ourselves. So the derivative of sine of x is cosine of x. Parentheses are good. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. And then the reciprocal functions, the derivative of cosecant of x is negative cosecant of x times cotangent of x. The derivative of secant of x is secant of x times tangent of x. And the derivative of tangent of x, cotangent of x is cosecant squared of x. Wow, I'm really blowing it here. Cosecant, squared of x. That's a cosecant, believe it or not. That looks terrible. Sorry. Cosecant. Okay. So writing this down, you automatically know 6 integrals, right? We know that the integral of cosine of x is equal to sine of x. And I'm not going to say the integral of negative sine is equal to cosine. I'm going to say that the integral of sine of x is equal to negative cosine of x. And yes, I should put on a plus c. And the integral of secant squared of x is equal to tangent of x. And the integral of cosecant of x times cotangent of x is equal to negative cosecant of x. And the integral of secant x times tangent x is equal to secant of x. Also plus c, plus c, plus c. And lastly, the integral of cosecant squared of x. Oh, I forgot the negative sign too. Terrible. I should have said the things I was about to start. So, well, let me finish. Let me do this here. So one thing to observe, which I should have said because I would have noticed, is that every cofunction, cosine, cosecant, and cotangent has a negative in their derivative. So yes, the derivative of cotangent x is negative cosecant squared of x. So the integral of cosecant squared dx is negative cotangent of x. Okay, but then there are 4 other integrals we need to know, or we probably need to know. The integral of tangent of x is either the negative natural log of the absolute value of cosine of x, or the positive natural log of the absolute value of secant of x. Either answer is perfectly acceptable. Some people just prefer one way versus the other. In a similar way, the integral of cotangent of x is the natural log of the absolute value of sine of x. And there typically is not an alternative way of writing this. Technically, if you wanted to, you could write it as the negative natural log of the absolute value of cosecant of x. Nobody writes it that way. I will point out, you can check this. What's the derivative of the natural log of sine? Oh, the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Oh, 1 over sine times cosine is cotangent. So the derivative of this really is that. The derivative of this really is that. It also works for secant, right? The derivative of the natural log of secant is 1 over secant times the derivative of the secant. But the derivative of secant is secant times tangent, so the secants cancel and you get tangent. It really works whether you write it this way or this way. It's kind of cool. Okay, then there's 2 more, which I think I can fit in here. There's the integral of secant. Let me write it up here. There's a little more room. So the integral of secant of x is equal to the natural log of the absolute value of secant of x plus tangent of x. Let's see. And the integral of cosecant of x, there are actually 2 ways of writing this one as well. It is either written as the negative natural log of the absolute value of cosecant of x plus cotangent of x, see, or the positive natural log of the absolute value of cosecant of x minus cotangent of x. And it can be shown that these are equivalent to each other. I don't think you need to show that. But so I should point out though, right? That this answer here, negative natural log of cosine, really is the same as the natural log of secant. All you're doing is you're taking that -1 coefficient and you're saying, oh, well, that's equal to the natural log of the absolute value of cosine of x to the -1 power. But then being raised to the -1 power is just a reciprocal. This is really the natural log of the absolute value of 1 over cosine of x. But 1 over cosine of x is secant of x. So that's what's happening here. That's why we're able to say that this is the same as this. In a similar but crazier way, you can show that if you bring this -1 up as the power here, that the reciprocal of cosecant of x plus cotangent of x, so 1 over cosecant plus cotangent, with some trig identities, you can show that 1 over cosecant plus cotangent is equal to cosecant minus cotangent, which is kind of neat. I've always liked that trig identity. So here are all of the trig integrals you might need to know. Specifically, the ones you might not have been aware of before, the integral of tangent being the negative natural log of the absolute value of cosine, or the positive natural log of the absolute value of secant, the integral of cotangent being the natural log of the absolute value of sine, the integral of secant being the natural log of the absolute value of secant plus tangent, and the integral of cosecant being the negative natural log of the absolute value of cosecant plus cotangent, or the positive natural log of absolute value of cosecant minus cotangent. I don't know if you absolutely have to know these, but it doesn't hurt to see them. If you don't have to know them, then just forget them. But yeah, well, that's all. Okay. Let's see what times. Oh yeah, we got. Let's look at the next one. So let's look at, that was problem 6. Let's look at 7. 7 looks like a tricky one. Integral of 1 over x plus the square root of x. So u sub doesn't look great, but after I consider and maybe dismiss u sub, I'm not really left with any other options. I can't use integration by parts because it's not a mixture. I can't really use I can't use partial fractions because it's not a rational function. So if I thought of u sub and dismissed it, and then kind of, I can't really simplify this, right? There's not a lot of other options. I'm kind of stuck, and I have to kind of go back to u sub. So yeah, what am I going to try here? This is where you have to get creative. So I might try letting, letting u equal x plus root x does not seem like a great idea. Because if I do that, my du is going to be 1 plus the integral, the derivative of the square root of x is 1 over 2 root x. That's kind of how I prefer to write. Right? You could write it as 1/2 x to the negative 1/2. I think this is usually better. And that doesn't look great, right? I don't see how I'm going to make that look like that. So that seems bad. So then I might try letting u equal a part of that denominator. So let's try letting u equal maybe just the square root of x. My du still isn't going to be great. My du is, again, 1 over 2 root x dx. Doesn't look very promising. It actually is somewhat promising, but I'm kind of hiding that fact at the moment. Would I do that? Yeah, I probably would. I would probably make this problem too hard. So let me show you what direction my brain would probably go first. I would do this thing where you solve for x, so square both sides, and then u squared equals x, and then taking the derivative of both sides, 2u du is equal to dx. So I could do that, and I could rewrite this as the integral of, so my dx is 2u du, and my denominator is u squared plus u. I guess I could factor out a u now. That's actually going to totally work. That works just fine. So then if I factor out a u from the top and the bottom, well, I suppose I could factor out a u from the bottom. Cancel a u there and there. This actually isn't so bad. So I get the integral of 2 over u plus 1, which is 2 times the natural log of the absolute value of u plus 1 plus c, which is 2 times the natural log of the absolute value of the square root of x plus 1. So a lot of the time, if you're kind of stuck with u sub but it doesn't look great, one trick is to, after you've made your choice for u, solve for x and then find dx in terms of du. Now I should mention there is another way of doing this problem. I just don't think it's as easy to see. So an alternative way of doing this is to look at this fraction and factor out a square root of x from the denominator. To me, that just doesn't feel very intuitive. But if I factor out a root x, I'm left with a root x plus 1. And then you can let u equal the square root of x plus 1. Right, but this I don't know. I feel like this just feels like I would never think to do that. I would never be like, yeah, factor out the square root of x. But it does work. If you let u equal the square root of x plus 1, then your du is, again, 1 over 2 root x dx. And then your 2 du is equal to 1 over root x dx. So then you've got, right, there's your dx over times 1 over root x. That's my du. So I'm going to have, or sorry, my 2 du. So it's going to be integral of 2 du over u. And then that's going to be 2 natural log absolute value of u, which is going to equal 2 natural log absolute value squared of x plus 1. Same answer. I would never think to do it this way. Like, probably, I mean, I might, like, if I didn't think of doing it this way, I'd be like, well, we'll try factoring something out, right? Like, but it feels very, very not like the way I would think to do it. But if it works for you, whoops, right? If you would think to do that, sorry, then you should do that. Let's look at this next one, which is similar but different. Let's say now we have the integral of x over 1 plus the square root of x. And again, I'm going to start by letting you equal the entire denominator. I know I tried that last time, it didn't really work out. It's still usually where I start out if I have a fraction like this, where I know partial fractions is not going to work, right? Can't do integration by parts, can't do partial fractions. It's kind of stuck with u sub. So there's my u. Again, finding du not super helpful, right? Du being 1 over 2 root x dx. It doesn't get me anywhere, right? I don't have a 1 over root x times x, right? I can't break this root x away from that 1 there. They're stuck to things in the denominator are always kind of stuck together. Right? We cannot disassociate them from each other. So instead, just like before, I'm going to solve for x. So square both, don't square both sides. Subtract 1 from both sides. U minus 1 equals the square root of x, and then square both sides. So I end up with, I'm gonna write x equal to u minus 1 squared. And I'm just gonna leave it as u minus 1 squared. So now I'm gonna find dx. My dx is going to be 2 times u minus 1 times du. Right? I'm literally just differentiating both sides. Derivative of some stuff squared is 2 times my stuff to the first times the derivative of my stuff. And now we're going to replace dx with 2 times u minus 1. So this is going to end up equaling. So just let's do dx first. There's my 2 times u minus 1. Great. There's my dx. Make sure we're all super clear about that. It's always the part when I'm doing a u sub that I'm most concerned with changing first. Always dealing with making sure dx converts to something with du in it. Right? You need the du there. That's important. Great. So that's my dx there, including the du. Great. And then everything else I'm just going to replace with what it's equal to. So x is equal to u minus 1 squared. And 1 plus root x is equal to u. Cool. So now I'm going to factor out the 2. U minus 1 squared times u minus 1 is u minus 1 cubed. There's a quick way for multiplying out something plus something to the third power. You can use Pascal's triangle. Those are the coefficients right there. This is going to equal 2 times the integral of 1 times u cubed plus 3 times u squared times -1 plus 3 times u times -1 squared plus 1 times -1 cubed. All divided by u. So that's going to equal 2 times the integral of u cubed over u is u squared minus 3u squared over u is minus 3u plus 3u over u is plus 3 minus 1 over u. And then we integrate the whole thing. We get u cubed over 3 minus 3u squared over 3, sorry, over 2 plus 3u minus the natural log of the absolute value of u. Well, it's kind of a problem. Let's see. And then we plug in u and we get 2 times 1 plus root x cubed over 3 minus 3 times 1 plus root x squared 2 plus 3 times 1 plus root x minus the natural log of the absolute value of 1 plus root x. A lot. Time is it? Yeah, we got time. We should do more problems. So that's it. It's kind of a beast of a problem while we're multiplying out. Let's look at looking at some convergence or divergence. So does the following integral converge or diverge? And although I'm not saying it, if someone asks you if an integral converges or diverge, well, actually, technically you could ask this question and not ask for what it converges to. Usually you're going to be asked if it converges to find what it converges to. So let's look at this first one. We have the integral from 1 to infinity of e to the negative 1 over x squared dx. Which I know I'm going to write as the limit as b goes to infinity of the integral from 1 to b of e to the negative 1 over x squared dx. I should point out, if this integral had been worse, if it had been the integral from 0 to infinity, I'd have to break it up somewhere between 0 and infinity, probably at 1, although anywhere would be fine, because 0 and infinity are both problem points, because 0 is where this function is defined. It's not, but if you do have more than one problem point, you do have to break it up. And then I really don't want to do this integral with all this jazz associated with it. I want to just off on the side. I just want to find the antiderivative of e to the negative 1 over x squared. I'm going to try a u sub. I could try u sub or erase my parts. I'm going to do a u sub first because that's always my preference to try u sub. I'm going to let u equal negative 1 over x, right? It's something that's stuck somewhere else, or negative x to the negative first. My du is exactly what I need it to be. It's going to be positive x to the negative second, or 1 over x squared dx, which I totally have. So this integral is going to become just the integral of e to the u du. That's great. That's just going to equal e to the u, which is e to the negative 1 over x. So I don't want to write the limits of integration with the limit while I'm trying to do that u substitution. So now I'm saying this is equal to the limit as b goes to infinity of, well, the integral of e to the negative 1 over x squared is e to the negative 1 over x from 1 to b. Then we plug in the limits of integration. We get e to the negative 1 over b minus e to the negative 1 over 1. And now we have to ask ourselves, okay, as b goes to infinity, what does this do? Well, as b goes to infinity, 1 over b goes to 0. And so I'm going to get e to the 0 minus e to the negative 1, which is 1 minus 1 over e. So this converges. And it converges to that value. You can just say converges to 1 minus 1 over e. You don't have to say it converges and it converges to this, right? Saying it converges to that means it converges. Yeah. Not too terrible a problem. Let's look at another one. So this is A. Let's look at B. Let's look at the integral from 1 to e of dx over x natural log of x. Whoops, I wrote dx twice. All right. Integral from 1 to e of dx over x natural log of x. So if someone didn't tell you that this was improper, you might miss it. But this definitely is improper because that integral is undefined. Or I should say the function inside the integral, the integrand, is undefined when x equals 1. Natural log of 1 is 0, and we can't divide by 0. So we do need to rewrite this as the limit as a approaches 1 from the right of the integral from a to e of dx over x natural log of x. And I would say it's definitely important to get the right side of this, meaning if I'm between 1 and e, I have to be approaching 1 from the right side because I'm bigger than 1. Okay, so then just like before, I'm going to do the integral off to the side, integral of dx over x natural log of x. U is going to equal the natural log of x, du is 1 over x dx. This integral is going to become the integral of 1 over u du, which is the natural log of the absolute value of u, which is the natural log of the absolute value of the natural log of x. So great, now I can write this as the limit, if a approaches 1 from the right, of the natural log of the absolute value of the natural log of x from a to e. And we can plug in our limits of integration. So limit is a approaches 1 from the right of the natural log of the absolute value of the natural log of e minus the natural log of the absolute value of the natural log of a. All right, so now the natural log of e is 1, and then the natural log of 1 is 0. So that part's going to be 0. And then the natural log of, so if a is approaching 1, the natural log of 1 is 0. And then if this part's approaching 0, the natural log of something approaching 0 is approaching negative infinity. So this part here is going to negative infinity. So we end up with 0 minus infinity, which is infinity. So this one definitely diverges. And specifically, it diverges to infinity. Sometimes they will ask you how it diverges. Like, does it diverge? If it diverges, does it diverge to infinity or to negative infinity, or can we not tell? Because you cannot tell, like if you have two different pieces, like you had to break it up into two pieces, and one of them is going to positive infinity, one of them is going to negative infinity, we're adding those together. It's indeterminate, we don't know. Let's look at the last one of these and then we'll call it a day. The last one of these converge or diverge questions. So we have the integral from 0 to 3 of 2x over x squared minus 1 to the 4th. Okay. And so where do we need to break this one up? What's our problem point? Not 2. Sorry. Yeah, it is 1. Because if we plug in 1, right, it's going to be 1 minus 1 in the denominator. So we definitely need to write this as the integral from 0 to 1 of 2x over x squared minus 1 to the 4th, plus the integral from 1 to 3 of 2x over x squared minus 1. And before I start writing out all the limits and stuff, let's just do the integral real quick. So the integral of 2x over x squared minus 1 to the 4th dx. It's going to be a u sub. We're going to let u equal x squared minus 1. Du is 2x dx. This is going to be the integral of du over u to the 4th, which is the integral of u to the negative 4th du, which is going to be u to the negative 3rd over negative 3, or negative 1 over 3u cubed. So I can see what's going to happen. I can see that I'm going to integrate this. I'm going to get negative 1 over 3 times x squared minus 1 cubed. And then when I plug in the 1, I'm still going to have division by 0. So I'm pretty sure this whole thing's going to diverge. And it looks like it's going to diverge whether I do this one or this one. So I'm going to do the first piece, and then we'll talk about kind of what we need to show here. So the limit as b approaches 1 from the left of the integral from 0 to b of 2x over x squared minus 1 to the 4th dx. That's going to equal the limit as b approaches 1 from the left of, well, we did the integral already, right? It's just negative 1 over 3 times x squared minus 1 cubed from 0 to b. And then that's going to be the limit as b approaches 1 from the left of negative 1 over 3 times b squared minus 1 cubed minus -1 over 3 times -1 cubed. Okay, so when we plug in 1, we're going to get 0 in the denominator. So we're going to get some sort of infinity. If we're having to answer the question about in which way it diverges, we probably have to be a little more specific here. So if I plug in the 1, and by putting 1 from the left, I'm a little smaller than 1. So a little smaller than 1 minus 1 is a slightly negative number. Slightly negative number cubed is still negative. And then we have a negative over a negative. So this is going to be a -1 over a -0. I don't really care about this other part, but it is minus -1/3. Negative over negative is a positive infinity. So this first portion diverges to positive infinity. The second portion, so this part over here, is going to be the limit as a approaches 1 from the right of the integral from a to 3 of 2x over x squared minus 1 to the 4th. And let's cut to the chase. We know we're going to integrate it and we're going to plug in 3 first and a second. So it's going to be the limit as a approaches 1 from the right. I plug in 3 to the antiderivative. I'm going to get -1 over 3 times 9 minus 1 cubed minus, when I plug in a, I'm going to get -1 over 3 times a squared minus 1 cubed. Okay, and now I'm going to think about it. So I don't care what this first number is, it's something. This is going to be, so if I plug in a number slightly larger than 1, it's going to be slightly larger than 1 minus 1, so still positive. Cube it, still positive. Times 3, still positive. And then minus is still positive. So it's going to end up being also positive infinity. So this does diverge to positive infinity.